Hello, we've got a video today about an alkenes past paper question. It's predominantly on synthesis. The synthetic techniques included in this question are distillation, the use of a separating funnel, drying agents and percentage yield. Other techniques which are used for synthesis and purification are reflux, recrystallization including the use of a Buchner filtration, melting points and boiling points, and chromatography. So you should be familiar with all these techniques. There's also a mechanisms question at the very end. As always, if you want to have a go at any part of the question, just pause the video. The format I like to use is black is the question, blue is the model answer, and red is any additional information. So here's the first part of the question. Have a little look at that. Pause the video if you like and press play when you're ready for me to go through the answer. Okay, so we've got part of a distillation apparatus shown and we need to complete the diagram. Although it doesn't tell us in the question, the cyclohexanol will have a higher boiling point than the cyclohexene. Cyclohexanol can make hydrogen bonds, whereas the cyclohexene cannot. So we need to just add the apparatus. We need a thermometer and a bung, and it's important that you show that that's sealed at the top there so that any gases formed cannot escape. So that must be labelled up, thermometer, and the bung also has to be labelled up as well. And the diagram must show, as I say, it must show that it's a sealed system at that stage. We then have to put on the condenser, label up that it's a condenser, and it's essential that we put in the water going in at the bottom and out at the top. The other thing that you must be aware of is that the bottom of the thermometer is at the junction, if you like, between where the gas can condense and roll down or can dribble down the condenser. So that's why I put that dotted line in there. Okay, so here's the next part of the question if you want to pause it now. Welcome back. So we've got some sodium chloride solution which we've shaken our substance with, and we've also now put it in a separating funnel, and we need to figure out why the two liquids can be separated. A separating funnel is used to separate two what we call immiscible liquids, or two liquids which will not dissolve in each other. This is usually once again linked to hydrogen bonds, and so the cyclohexene that we've produced is going to be in the what we call the organic layer, and the other substances will remain in the aqueous layer. So the reason why they can be separated is that they are immiscible. They do not mix, they do not dissolve in each other. Reason for that is extra information there is the cyclohexane will not make the hydrogen bonds with water. Okay, take a look at the next part of the question, pause it, press play when you are ready. The cyclohexene separated was a cloudy liquid, and so the student is going to add a few lumps of anhydrous, that means without water, anhydrous calcium chloride. This is a drying agent, so any molecules of water that are present in our cyclohexene can be removed using our drying agents. What happens is the calcium chloride anhydrous will turn into calcium chloride hydrated, including those molecules of water of crystallization. It's often a giveaway that if an organic liquid is cloudy, that it must be what we would call wet, or it must contain some water. If it goes clear, it means that we've removed that water. So that will be the observation once the cyclohexene is dry, that it will no longer be cloudy. Okay, so a yield question next. Pause the video, have a go, press play when you're ready. Welcome back. Most important thing with all calculations is setting out your working out clearly to ensure that you get method marks, especially with these longer questions. So this one, as you can see, is 5 marks. So we've abridged the question here to get right to the important thing. The balanced equation is going to be a 1-to-1 reaction. You're not asked for the balanced equation, but I do think it helps. The amount of the alcohol, the amount of the alkene, the amount of the alkene actual, so theoretical and actual, and finally the percentage yield. We can just use those to kind of as a map to getting towards getting from the beginning to the end of the question. The amount of the alcohol is worked out by mass over molar mass. The amount of the alkene, because it is a 1-to-1 reaction, is the same as the amount of the alcohol. That's theoretically, assuming 100% yield. The actual amount of the alkene that we get is again mass over molar mass, and percentage yield is given by that equation, actual divided by theoretical times by 100. That can be actual and theoretical amounts in moles or masses in grams, as long as you're consistent. So let's take a little look at the numbers. The 14.4 over 100 is from the question for the amount of alcohol, and that works out at 0.144 moles. And that's the same amount of the alkene that you would expect to get from a 100% yield. We need to use the density and the volume of the cyclohexene to work out the mass, so that's where the 4.15 times the 0.810 was come from, and that gives us the amounts of the alkene that we actually obtained. Now we put those numbers for actual and theoretical into the yield calculation, and we can work out that it's 28.5%. Okay, so the final part of this question is a mechanism. Pause the video and press play when you are ready. Welcome back. So we've got a mechanism. Remember what Curliado showed, the movement of a pair of electrons, which is always linked to bonds breaking or bonds forming. We've got an alkene, so electrophilic addition in this case. The delta positive and delta negative can be put on that bromine molecule, so a dipole is induced as soon as the bromine molecule approaches the carbon-carbon double bond. The carbon-carbon double bond breaks, and those pair of electrons from that double bond go to form a bond with the bromine, and the bromine to bromine bond, that black arrow, that's showing that that bond is breaking. That makes that intermediate. Now this question requires us to use skeletal formulae, so as the bond breaks we can put the bromine on either of the carbons in the carbon-carbon double bond, and where the bond was broken, the other carbon has received a positive charge. The bromide ion is also produced in that first step. You can see there the lone pair of electrons on the bromide, and it's got a negative charge, and those lone pair of electrons can now be donated to form a full covalent bond, making the dibromohexane, the 1,2-dibromocyclohexane molecule.